Hello, my name is Laura Serra. I have a degree in mathematics and a PhD in statistics. In this video, I'm going to talk about how to implement linear regression with R. Then, I'm going to present the main instructions for running this basic and commonly used type of predictive analysis. As I have mentioned in the theoretical part, the main goal of regressions is to explain an outcome variable depending on others and in what way do they impact the outcome variable. Let's continue working with the database about pregnant mothers with a single pregnancy followed in vitro fertilization. We are going to see how to run with R a linear regression model that explains the weight of the newborn based on variables related to the mother, such as maternal age measured in years, the gestational age expressed in weeks, the birth order of child, and number of cigarettes per day. I remember that the sample includes 641 pregnant mothers with a single pregnancy following in vitro fertilization. As we saw in previous sessions, first, we must specify the working directory where we have the database with which we want to work, and then load the data and activate it. In this case, we have the data in the CSV format, so the instruction is as follows. We can also display the name of the variables in the database by typing names, break data. The dependent variable in the regression model that we will adjust is birth weight in grams, and the explanatory variables are maternal age in years, gestational age in weeks, birth order of child, and number of cigarettes per day. In any regression study, it's important to know how the variables are intended to be analyzed. In a first analysis, the descriptive statistics of each one of the quantitative variables of the study are studied. The instructions in R for running descriptive statistics are summary, which give us the minimum value, the quantiles, first, second or median, and third, the mean, the maximum value, and the number of NAs. Parallel to the numerical information resulting from the descriptive statistics, the graphics are another very useful tool that completes the exploratory analysis of the data. The univariate graphs allow to visually detect the characteristics of asymmetry and the outliers of the study variables. These graphs are also very useful to decide if the logarithmic transformation of numerical variables is necessary. Instructions for running univariate graphs are box plot. In general, looking at the 5 figures, it's observed that the data of the variables are symmetrical, except for figure 5, presenting a slight positive asymmetry, but it's not remarkable. So, logarithmic transformations are not necessary, which are useful when the low values are concentrated and the high dispersed. A strong positive asymmetries and atypical values on the high side. Regarding outliers, quite a few are observed in the lower part of figure 3 and 4, as well as one in the upper part of figure 3. We will have to study and treat them in case they are influential values and therefore modify the results of analysis. However, all the cases and improvements of the linear regression model escape the objective of this introductory theme. To complete the exploratory analysis and to know the degree of relationship between the explained variable and the regressors, it's interesting to make graphs of dispersion between the dependent variable, birth weight in grams, and the explanatory variables. These graphs give a first idea of the relevance of each independent variable in relation to the dependent variable. It's a first approach to the fulfillment of the assumptions and more clues as to whether any variable should be transformed. The corresponding instruction is plot. Within the parentheses, the first variable will be represented on the horizontal axis and the second variable on the vertical axis. The dependent variable is always represented on the vertical axis, so let's write it in second place. In a visual way, we can say that only figure 2 indicates a positive linear relationship between the gestational age and the dependent variable. The rest of them show a fairly weak relationship between the two variables, especially figure 4, which shows a practically null relationship between the two variables, since no linear pattern is perceived between them. This fact indicates that the variable parity seems to have no influence when explaining the dependent variable. In addition, these graphs also inform us that no chart shows a concentration of low values accompanied by a dispersion of high values, so any variable needs to be transformed to a logarithm. To confirm the relationship between the explanatory variables and the dependent variable, one can also turn to the computation of the correlation coefficient that can confirm or disprove what is visually observed in the figures. The correlation coefficient, as already explained in a previous session, is a value between -1 and 1 that informs us about the degree of dependence between two variables. Then, we can observe how, in this case, figure 2 presents a value over 0.7 indicating an important dependence between the variables, as it could already be seen in a visual way. With respect to the other graphs, the correlation coefficient decreases. We see that indeed the relationship between the dependent variable and the maternal age or the number of cigarettes variables is lower, given that the correlation coefficient is reduced by more than half compared to figure 2. So they indicate a weak dependent relationship. Finally, figure 4, as we saw in the graph, shows a very low correlation value, confirming the independence between the two variables. This first descriptive analysis of the data gives us some light about which are the most relevant variables for the study and which could be superfluous. The aim is to adjust the best linear regression model that explains the weight of newborns considering the maternal age, the gestational age, the birth order of child, and the number of cigarettes per day. Therefore, it's a multiple linear regression model that includes 4 explanatory variables. The instructions in R to adjust the linear model are the following. The instruction creates an object of type model that we decided to call model from a linear model, LM, based on the econometric methods of ordinary squares minimums, where the birth weight is the dependent variable and the ones that follow behind the symbol is the list of explanatory variables. It's important to note that the instruction ni.action equal ni.exclude is added in the model since there are missing values in the variables and thus they are excluded from the analysis. The instruction LM doesn't give any results. It's the summary instruction that gives all the results of the regression, a description of the errors, the estimated coefficients of the betas with its standard error, statistics and significance, the measures of goodness of fit and global contrast. As already mentioned in the previous session, regression models have to fulfill some assumptions, which is what we call validate the model. Thus, the validation of the model consists of analyzing if the assumptions of the linear regression models are met. In particular, the diagnosis of the final model is based on residual analysis, which is based on verifying whether the assumptions about the term of error are met. As the error is not known, an approximation is used that we call studentized residuals, which are the ones used for the verification. The first assumption tries to verify if residuals are distributed around 0. Then, the idea is to graphically represent the studentized residuals with each of the regressors. You can build the graphs of the studentized residuals with each one of the regressors and see that they are distributed around 0 in all the zones of the graph. To simplify the graphical reading, a horizontal line can be drawn on this level. The necessary instruction is a blind break age equals 0. With R, the necessary instructions are the following. The graph shows an example considering the explanatory variable maternal age in year and the studentized residuals. To validate the first assumption, we will have to repeat these instructions for each of the explanatory variables. After checking it for each of the regressors, it seems that the assumption is true in all cases, since there is no systematic behavior and the values are randomly distributed around zero. The second assumption is homoscedasticity, which allows to determine if the variance of the residuals is constant. To detect compliance with this assumption, the student-type residuals are plotted with the predicted values to see that there is no variation in the dispersion of the residuals, vertical axis, in areas of the graph with different predicted values, horizontal axis. The instructions in R are the following. The previous graph doesn't show any pattern in the dispersion of the points that vary by areas of the graph. Therefore, one could say that the assumption of constant variance is met and that the model is homoscedastic. The other assumption is normality. The normal probabilistic graph of the student-type residuals are used to verify the assumption of normality. This graph represents each order value with the expectation of this value, assuming that the data come from a normal distribution, which is called normal scores. The more normal the distribution, the closer the point will be to the line that forms 45% with the axis. With the R software, the instructions that must be written on the console are the following. Although the cuckoo graph shows a very slight curvature at the ends of the diagonal, it can be affirmed that the assumption of normality is fulfilled and the results can be interpreted without any problem. In this case, given the size of the sample is bigger than 300, the assumption would not worry us even if it didn't comply. Finally, in addition to checking the compliance of the assumptions with respect to the residuals of the model, it's also necessary to analyze the existence of influential atypical values, which indicate the presence of inhomogeneous observations with the rest. To detect the influential outliers, Cook's distance is used, which provides a measure of the influence of the ith observation on the set of parameter estimates. The necessary instruction is the following. It's observed that there is no point that has a distance of Cook too prominent with respect to the rest. Once all the assumptions have been checked and the variables are significant, the last step is to interpret the model and make forecasts. As mentioned, the instructions for running a linear regression model are LM, and if we assign a name to this LM object, such as model, then we need to write summary break model to see the output. Then, what we get is the value of the parameters, the betas, which appear below the column headed by estimate, with the respective standard errors, the t-statistics, and its corresponding associated p-value. Looking at the results, it can be concluded that only one variable, the gestational age, measured in weeks, can be interpreted, as the rest of the explanatory variables are not significant, with a p-value bigger than 0.05. This result could already be intuited with the initial descriptive analysis, since we have seen that only gestational age had a clear relationship with the dependent variable. Then, from here, we can consider re-estimating the model by removing some of the non-significant variables of the model. Always look for the most parsimonious model possible, so adding superfluous variable in the model is not recommended. However, this exceeds the goal of this chapter. The way to interpret the only significant coefficient is as follows. An increase of 1 unit, weeks in this case, in the gestational age implies an expected increase of 26.484 grams in the weight of the newborn, keeping the rest of the variables constant, which is called ceteris paribus. However, interpretation is more accurate if the confidence intervals are used, which can be obtained with this instruction. So, with 95% confidence, an increase in 1 week of the gestational age implies an increase in the weight of the newborn between 191.4 221.76 and 221.21. Another information that can be obtained from the output on the estimation of the linear regression model is the R-square that tells us how much the model explains to us. That is, it's the value that tells us the percentage that the model explains of the variance of the variables explained, in this case, the weight of the newborn. In particular, we can see the R-square and the adjusted R-square, which is more accurate. In this case, the model explained around 54.2% of the variance of the weight of the newborn. We see that it's not the best model we could have estimated, but it explained a fairly acceptable percentage of the dependent variable. But nevertheless, the next step could be to try to estimate another model, eliminating, for example, the variable parity that we have seen that was not significant, and see if the model improves. This, but would be in a later course. Thank you very much for your attention, and I'm waiting to answer questions or queries that you may have. A pleasure to have shared this hour with you.